calculation performed to determine the required kilovolts for power factor correction is correct and provides a reasonable estimate. The steps include determining the angle difference represented as delta theta between the original power factor and the desired power factor, then calculating the kilovolts using the formula kilovolts equals kilowatts times the tangent of delta theta, and finally substituting the values to solve for kilovolts. In the example given, a 100 kV capacitor would theoretically be sufficient to improve the power factor to 97%. However, the size of the capacitor needs to be justified. Factors to consider include capacitor size, harmonic distortion, and load fluctuations. A 100 kV capacitor is relatively large for a 300 kV substation and may cause voltage spikes or other issues during switching. Toy manufacturing equipment may generate harmonics, which can distort the power factor measurement and affect capacitor performance. The actual load and power factor vary over time, which can impact the effectiveness of the capacitor. Instead of installing a large capacitor, alternative solutions may be explored. Firstly, multiple smaller capacitors, for example 20 kVAr or 30 kVAr, can be installed in parallel to achieve the desired kilovolts without overloading the substation. Secondly, dry-type transformers with better efficiency may be considered. Dry transformers have higher power factors, which can reduce the overall kilowatt demand. Thirdly, if harmonics are an issue, installing harmonic filters can mitigate their impact on power factor correction. In conclusion, the calculation provides a starting point for power factor correction. However, it is important to consult with a qualified electrical engineer to determine the optimal solution considering the specific factory conditions and equipment. It's important to delve into the concepts of power factor, reactive power, and the implications of harmonic distortion to fully grasp the situation. Power factor is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. It represents how effectively electrical power is being used. A power factor of 1.0 or 100% indicates perfect efficiency, where all the supplied power is used for doing useful work. A lower power factor means that a larger amount of apparent power is required to supply the same amount of real power, leading to increased current flow, higher losses, and reduced system capacity. Reactive power, measured in kiloVars, is the power required to establish and maintain magnetic fields in inductive loads, such as motors, transformers, and fluorescent lighting ballasts. Unlike real power, reactive power does not perform any actual work but is essential for the operation of inductive devices. A lagging power factor, which is common in industrial facilities with many inductive loads, indicates that the current lags behind the voltage. Power factor correction involves adding capacitors to the electrical system to compensate for the reactive power consumed by inductive loads. Capacitors generate reactive power, which counteracts the reactive power drawn by the inductive loads, bringing the power factor closer to unity. By improving the power factor, the amount of current required to deliver the same amount of real power is reduced, leading to several benefits including reduced energy losses in the distribution system, improved voltage regulation, increased system capacity, and lower electricity bills. Harmonic distortion is a phenomenon that occurs when nonlinear loads such as electronic devices, variable frequency drives, and arc furnaces draw current in a non-sinusoidal manner. These non-sinusoidal currents introduce harmonic frequencies into the electrical system, which are integer multiples of the fundamental frequency, typically 60 Hz in the United States. Harmonics can cause various problems, including overheating of transformers and conductors, malfunction of sensitive electronic equipment, and inaccurate power measurements. When performing power factor correction, it is crucial to consider the presence of harmonics, as they can affect the performance of capacitors and lead to resonance conditions, which can amplify harmonic currents and voltages, causing equipment damage. To mitigate the effects of harmonics, harmonic filters can be installed. Harmonic filters are designed to block or reduce the flow of harmonic currents, preventing them from propagating throughout the electrical system. There are several types of harmonic filters, including passive filters, active filters, and hybrid filters. Passive filters consist of inductors, capacitors, and resistors tuned to specific harmonic frequencies. They provide a low impedance path for harmonic currents, diverting them away from the rest of the system. Active filters use electronic components to actively inject harmonic currents that cancel out the harmonic currents produced by the nonlinear loads. Hybrid filters combine passive and active filtering techniques to achieve optimal performance. When selecting a capacitor for power factor correction, several factors need to be considered, including the required kiloVars, the voltage rating, the current rating, and the harmonic content of the electrical system. The required kiloVars can be calculated using the formula mentioned earlier, taking into account the desired power factor and the existing power factor. The voltage rating of the capacitor should be equal to or greater than the nominal voltage of the electrical system. The current rating of the capacitor should be sufficient to handle the reactive current that it will generate. The harmonic content of the electrical system should be analyzed to determine if harmonic filters are needed to protect the capacitor from harmonic currents. The location of the capacitor is also important. Capacitors can be installed at various points in the electrical system, including at the individual loads, at the distribution panels, or at the substation. Installing capacitors at the individual loads provides the most effective power factor correction, as it reduces the current flow throughout the entire system. However, this approach may not be practical for large facilities with many loads. Installing capacitors at the distribution panels provides a compromise between cost and performance. Installing capacitors at the substation provides the least effective power factor correction, as it only reduces the current flow from the substation to the distribution panels. In the case of the toy factory, the maintenance engineer is concerned about the size of the 100 kV capacitor is valid, as it may be too large for the 300 kV substation. A smaller capacitor or multiple smaller capacitors in parallel may be a better option. It is also important to consider the harmonic content of the electrical system, as toy manufacturing equipment may generate harmonics. If harmonics are present, harmonic filters should be installed to protect the capacitor and prevent resonance conditions. Furthermore, it is essential to monitor the load fluctuations and power factor over time, as they can impact the effectiveness of the capacitor. If the load and power factor vary significantly, a dynamic power factor correction system may be needed. A dynamic power factor correction system uses automatic switching to adjust the amount of capacitance based on the changing load conditions. In addition to capacitors and harmonic filters, other technologies can be used to improve power factor, such as synchronous condensers and static VAR compensators. Synchronous condensers are rotating machines that generate or absorb reactive power, providing dynamic power factor correction. Static VAR compensators are electronic devices that use thyristors to switch capacitors and inductors, providing fast and precise power factor correction. When implementing power factor correction, it is crucial to follow all applicable electrical codes and standards, such as the National Electrical Code, also known as NEC, and the Institute of Electrical and Electronics Engineers, known as IEE, standards. These codes and standards provide guidance on the safe and effective installation and operation of power factor correction equipment. Power factor correction is an important aspect of electrical system design and operation. By improving the power factor, energy losses can be reduced, voltage regulation can be improved, system capacity can be increased, and electricity bills can be lowered. However, it is essential to consider all relevant factors, such as capacitor size, harmonic distortion, and load fluctuations, to ensure that the power factor correction system is effective and reliable. Consulting with a qualified electrical engineer is highly recommended to determine the optimal solution for specific factory conditions and equipment. Remember that electrical systems are complex, and improper installation or maintenance of power factor correction equipment can lead to serious problems, including equipment damage, fire hazards, and electrical shock. Therefore, it is crucial to hire qualified professionals to perform all electrical work. To further elaborate on the impact of harmonics, it's important to understand how they propagate through the electrical system and interact with various components. Harmonic currents flow through the impedance of the electrical system, causing voltage drops at harmonic frequencies. These voltage drops can distort the voltage waveform, leading to various problems. For example, harmonic voltages can cause transformers to overheat due to increased core losses and eddy current losses. Harmonic currents can also cause conductors to overheat due to increased skin effect, which concentrates the current flow near the surface of the conductor. Sensitive electronic equipment, such as computers, programmable logic controllers, known as PLC, and medical devices, can be particularly susceptible to harmonic distortion. Harmonic voltages can interfere with the operation of these devices, causing malfunctions, data errors, and premature failure. Power measurement devices, such as meters and transducers, can also be affected by harmonic distortion. Harmonic currents and voltages can cause these devices to provide inaccurate readings, leading to billing disputes and incorrect system analysis. In addition to the problems mentioned earlier, harmonics can also cause resonance conditions in the electrical system. Resonance occurs when the inductive reactance of the system equals the capacitive reactance, creating a low impedance path for harmonic currents. When resonance occurs at a harmonic frequency, the harmonic currents and voltages can be amplified, leading to equipment damage and system instability. Harmonic filters are designed to prevent resonance conditions by providing a low impedance path for harmonic currents at specific frequencies. By diverting the harmonic current away from the rest of the system, harmonic filters reduce the risk of resonance and protect sensitive equipment from harmonic distortion. There are several types of harmonic filters available, each with its own advantages and disadvantages. Passive filters are the simplest and most common type of harmonic filter. They consist of inductors, capacitors, and resistors tuned to specific harmonic frequencies. Passive filters are relatively inexpensive and easy to install, but they can be bulky and may require periodic maintenance. Active filters are more complex than passive filters, but they offer several advantages. Active filters can dynamically adjust their filtering characteristics to adapt to changing load conditions. They can also mitigate multiple harmonic frequencies simultaneously. Active filters are more expensive than passive filters, but they offer better performance and flexibility. Hybrid filters combine the advantages of passive and active filters. They use a passive filter to provide a lower impedance path for the dominant harmonic frequencies and an active filter to mitigate the remaining harmonic frequencies. Hybrid filters offer a good balance between cost and performance. When selecting a harmonic filter, it is important to consider the harmonic content of the electrical system, the performance requirements, and the budget constraints. A harmonic study should be performed to determine the dominant harmonic frequencies and their magnitudes. The performance requirements will depend on the sensitivity of the equipment being protected and the level of harmonic distortion that can be tolerated. The budget constraints will determine the type of filter that can be afforded. In addition to harmonic filters, other measures can be taken to reduce harmonic distortion, such as using harmonic mitigating transformers, installing line reactors, and implementing power factor correction. Harmonic mitigating transformers are designed to reduce the harmonic currents that are generated by nonlinear loads. They use special core designs and winding configurations to minimize the flow of harmonic currents. Line reactors are inductors that are installed in series with nonlinear loads to reduce the rate of change of current. By reducing the rate of change of current, line reactors help to reduce the harmonic content of the current waveform. Power factor correction can also help to reduce harmonic distortion by reducing the amount of reactive power in the electrical system. Reactive power can amplify harmonic currents, so reducing the reactive power can help to mitigate harmonic distortion. Power factor correction is often implemented using capacitors, but it is important to select capacitors that are designed to withstand harmonic currents. Standard capacitors can be damaged by harmonic currents, so special harmonic rated capacitors should be used. The selection and implementation of power factor correction and harmonic mitigation equipment should be performed by qualified electrical engineers who have experience in these areas. Improper selection or installation of this equipment can lead to serious problems, including equipment damage, fire hazards, and electrical shock. It is also important to perform regular maintenance on power factor correction and harmonic mitigation equipment to ensure that it is operating properly. Capacitors should be inspected periodically for signs of damage, such as bulging or leaking. Harmonic filters should be tested periodically to ensure that they are providing the required level of filtering. Power factor correction and harmonic mitigation are important aspects of electrical system design and operation. By implementing these measures, energy efficiency can be improved, equipment reliability can be increased, and the risk of electrical problems can be reduced. The specific measures that are appropriate will depend on the specific characteristics of the electrical system and the loads that are connected to it. A thorough analysis of the electrical system should be performed to determine the optimal solutions. The National Electrical Code, or NEC, provides guidelines for the installation of capacitors and harmonic filters. NEC Section 460 covers the installation of capacitors, and NEC Section 470 covers the installation of harmonic filters. These sections provide requirements for the sizing, location, and protection of this equipment. It is important to comply with these requirements to ensure the safe and reliable operation of the electrical system. In addition to the NEC, there are also industry standards that provide guidance on power factor correction and harmonic mitigation. IEEE Standard 519 provides recommendations for harmonic control in electrical power systems. This standard provides guidelines for the limits of harmonic distortion that should be allowed in electrical systems. It also provides recommendations for the design and implementation of harmonic filters. IEEE Standard 141 provides recommendations for power factor correction in industrial and commercial power systems. This standard provides guidelines for the selection and application of capacitors for power factor correction. It also provides recommendations for the design and implementation of power factor correction systems. These standards can be valuable resources for electrical engineers who are designing and implementing power factor correction and harmonic mitigation systems. It is important to stay up to date on the latest versions of these standards to ensure that the electrical system is designed and operated in accordance with the best practices.